Good morning, good afternoon, good evening, depending on where you might be tuning in, and welcome to the first ever Mathematica Experts Live. I'm your host, Zach Parcell, and over the next hour, we will be taking your questions on the topic of visualization inside Mathematica. We're going to find answers to those questions from these Mathematica experts, and hopefully you will learn a few things. Now, we had a ton of questions submitted beforehand. We're going to try to get to as many as we can, but please feel free to submit questions, follow-up questions, whatever you wish, in the room itself, and we'll try to get to as many of those as we can. Let's introduce three colleagues of mine who will be doing the answering today. At the far end of the table, we have Yusung Cheng.
Hello.
Followed by Vitaly Korov.
Hi.
And finally, Brett Champion.
Hi.
You guys ready?
Yep.
Let's get it going. All right, first question, and try to get to as many of these as we can. Yusung, give this one to you to kick things off. Kind of a fun one. I'm making a game. I want to create an 8x8 array of random zeros and ones, visualize it with array plot, and replace the ones with a picture of an ant.
Okay, let me try. First, I have to get the ant picture right, so I'm going to search for some images. Let's try to choose this one. Looks good. So one great thing about Mathematica is you can just copy image and you use it in the program itself, right? So ants. I'm resizing it because it's probably way too big. So let me make it a reasonable size. And let's see. What the user is talking about is this. Random integer of 1 and zeros and 8x8. You get a nice matrix and you put the array plot on around it. What you're getting is, you know, the random checkerbox, right? And he want to turn these cells into the ants. Well, if it's a Brett, then he will come up with some crazy image processing way to do it, but I will just do it straightforward. So let me first think, you know, I will create ant plot with two parameters, right? One is matrix and another one is image. And I can take a bunch of options for it and see. It will be just a plain graphics wrap around with the options. So this is a start. But what I'm trying to do is creating a table of the I and, you know, in the dimensions of C and second element and the dimensions of the C in first element. The reason I'm flipping this second and first is because the you know, this graphic coordinate is kind of flipped there. Now what I'm trying to do is putting the ant images when the J and I component of the array is 1, right? That's only time why I want to do that. So mainly I'm using the function called insert, which is pretty neat. So you are essentially grabbing anything, it could be a text or anything, into the graphic scene. And the coordinate should be I, J. And let's say image has its own dimension. So, you know, how big, depending on how big image, I have to, you know, spread them out. So that's the coordinate I'm put the image on. And this is called the anchor point, where I'm going to anchor that images on particular that, you know, the ant image. Then the size of the image has to be specified too. So let me use the image dimensions again to specify the size. Let's try it, how it works. I think we are fine. Well, it's a lot of pressure here, so yeah. Let me try 8x8 matrix with, let's say, the ant, right? Hey, it worked.
Beautiful.
Right? But
nice.
Here's a kicker. Let me try the exactly same C here. Now the problem is, as you can see, this picture comparing with this picture, it's kind of flipped vertically, right? That's the way the array plot treat the coordinates. So to avoid that, I can just, you know, put the negation to the J, essentially flipping, you know, the Y coordinate. Now you get perfect picture. You can push it all the way to get more ants, right? Integer, let's say, 20, 20. Oh, not ants. Yep, I think this is enough.
Very good. All right, Vitaly, let's get you the second question here. Do you have any tips for speeding up the response of graphics, especially 3D graphics, when using Manipulate?
Oh, it's a very good question. I have it asked quite often. So basic thing here is to remember that it's important to track what kind of things we are changing inside Manipulate, what kind of variables, because defaultly, if you have a variable change inside Manipulate, it will change and recompute all the content inside the Manipulate function. So let me just try to invent a small application here. I will start with plot3d function. And I will grab some beautiful example from our documentation. Let's say this one. This looks quite nice. So as you see, when you get 3D graphics in Mathematica, you can interact with it immediately. You can rotate it, pan it around, and zoom in, zoom out. And when you do that, you can take a pick at options that you're actually changing. So here you have a set of options that you changed. And for example, one of them is viewpoint, another is view angle. And let's say we would like to create an application that showcases your graphics, changing these options, but not by hand manually, but automatically. So I'm going to stick this beautiful plot inside manipulate, and I'm going to add options to it. For example, I would say that my view angle, which is responsible for zooming in and zooming out, going to be variable s. And I'm going to also say that my viewpoint going to be depending on a variable t. I'm going to introduce a rotation around axis, vertical axis, to my picture with a fixed z coordinate. So, and I'm going to introduce now the variables themselves. So as original, the angle, view angle is in radians, so I'm going to put it like .35, which is close to default one, and go with a range from point, let's say 2 to 1.2. I'm just guessing this approximate range of parameters. And for t, I'm going to do the complete circle of spinning. And let's see, I would like to have my mesh on in this picture. So let me see what happened here. I think I'm missing.
Mouse over here and will tell us what the error message is. You've got an extra comma somewhere.
Yep. Yes, I see it. Here it is. So now we have our picture, and as you can see, the high quality graphics is on the screen. But if you start, for example, rotating it around or zooming in and zooming out, the mesh disappears and quality of graphics goes into a little bit minimal state to speed it up. Basically, it tells us that constantly when you change this variable inside manipulate, all the content getting recomputed all the time. So to avoid that, you just have to wrap dynamic around your functions. This will localize the variables s and t inside the manipulate only to these lines, only to these properties, and will not recompute this content. So if you reevaluate, now changing t and changing s does not change the quality of the graphics. And you, for example, can create an application which showcases your beautiful graphics, zooming in and spinning around it simultaneously without changing quality. So it's all about localization of variables inside manipulate.
Great. No, fantastic. All right. Well, I know, Brett, I know you're anxious to get a question here, so we'll get you one. Is it possible to label only specific contours in a contour plot?
Yes, it is. So we'll start with a simple contour plot, and we'll use contour labels. So it goes to all to label all the contours. But if this is more contours than you want, then we have a couple of options for how to reduce the number of contours that you see. So if you're just doing a single plot and you're not going to be doing lots of these, or you're not going to be regenerating it with different parameters, perhaps the easiest way is to, say, pick the ones that you don't want. Say, I don't like 0.6, and select it by clicking on it, hitting the delete key, and getting rid of it. If you click too far, then you get into a point where you can edit it. And so I can change this contour to say hello. And I just accidentally deleted the entire plot, but OK. But if you are going to be generating lots of plots or regenerating with different styles or tweaking it over time, it's probably easier to look into the advanced settings for the contour labels option. And so the main one that we're going to be interested in is this F form, which allows us to provide a function that takes X, Y, and Z information about the contour plot and generates labels. And so here we're going to create a function of X, Y, and Z. And suppose I want only 0.2, 0.4, and 0.8, and I don't want any of the 0.6s. So I'm going to write an if statement that if, okay, so these are all between 0 or -1 and 1, so I'm going to multiply them by 10 and round it to the nearest integer so that I can do more robust testing. So 10 times the Z value, the height. So if this matches, and I want 2 or 4 or 8. And I want to go ahead and I'm going to look at the absolute value of this to also pick up the negative numbers for that. So if we're going to match these contours, then we're going to put in a text primitive with Z at position XY. And otherwise, we're just going to include an empty list. And now we can see that I have a plot that has no of the 0.6 contours. And one additional point I want to make about contour plot is that, so we're plotting a product of trig functions, and this is going to have a maximum at 1 and a minimum at -1. And so we can't hit the actual maximum or minimum because those are basically points on this plot. And even if you had a contour plot where the maximum or minimum does correspond to an actual curve, you still won't be able to hit those as contours using contour plot. So,
fantastic. Well, we have a bunch of questions coming in, and keep sending those, and we're trying to get to as many as we can. We also had a bunch of questions pre-submitted that we wanted to make sure that we answered as well. So we're going to take a quick break, go to one of those, and when we come back, more of your questions here on Mathematica Experts Live.
Besides abundance of specific technical questions we received for this workshop, there were also quite a few questions of general character. It's of course understandable because some people perhaps just starting with graphics or Mathematica. I'm sure they would like to see examples of good practices, some inspiration, and possibly some exemplary code they can use for their own goals. Let's take a look at a few such questions coming from educators. First of them reads, I'm interested in meaningful graphics that will help me to create a more individualized student experience. Another one, I like to make figures in Mathematica for my courses. This job is time-consuming. What can be done to help this process? To partially answer this, I'd like to tell you about the Wolfram demonstration project. It's a free online publishing service dedicated solely to Mathematica code and applications covering a wide range of subjects. We have submissions from people all around the world, of various occupations and ages, who like you are Mathematica users. Every demonstration is an interactive app which runs live computation right in a web browser. You can guide computation via various controls, and the app content will respond fluidly. This is in-browser live computational interactivity, which is enabled by our latest technology called Computable Document Format, or shortly CDF. Every demonstration page has source code available free for download, re-embedding tools to put it on your own blog or website, and description of the content topic, which sometimes can be quite detailed, especially if the app is about classic educational subjects such as physics or math. As I already mentioned, we have very wide subject representation. For example, we could choose section mathematics, subsection algebra, subsection complex numbers, or life sciences, cognitive science, perception, and get quite a few related applications. Many subjects, from traditional to exotic, have their place on this site. All demonstrations are reviewed by our technical team, and many of them have 2D or 3D graphics. These are excellent source of inspiration for your own projects. Learn from them, reuse freely, as they are in your classroom for your lectures or homework, or adopting the code or its parts for your specific goals. No matter what you need, high chance you will find it among almost 8,000 complete examples. This collection keeps growing quickly, and we hope to see your work too as contribution to this great community project.
That was one of our pre-submitted questions. We'll have a few more of those to get through throughout the next hour. About 45 minutes left or so to take your questions about visualization inside Mathematica. And let's keep the questions going. Yusa, I think you're up next for one here. I use Mathematica to solve differential equations. The solution is a function of two variables, space r and time t. I'm interested in animating to display how the solution moves in time.
Yep, nice question, because we do that all the time, and it's extremely important to visualize, your differential equation, because that's key to understanding how the equation behaves. And I will show you the one example from our ND-solve documentation. It's based on Lorentz equation. Now let me solve this. Now it solves it in time as well as x, y, z, triple coordinates. So essentially what's happening is, according to time, the particle moves around the space. And I will try to draw it using parametric plot here. So let's see. The reason I'm putting evaluate inside is because this one. So this slash dot is our Mathematica's fancy way to replacing, in this case, the t, time, with the s, the solution, so that this x, y, g will be replaced by the interpolating functions here. So let me just try to plot it like this. Okay, it was easy, but the question about the animating this, right? There's a two way to go about it. One is, so you first we have to figure out, what is your target, whether it's an interactive animation or you're aiming for high quality. In this case, let's try the interactive one first. So it's pretty simple. Instead of going all the way to 200, you can go to the, let's say, until TT, where the TT varies from 1 to 200. Now, so it only draws up about that much, and you can control the TT to get the whole answer. Now, it's weird, right? It jiggles and everything, so I will get to that. Now, the first of all, when you drop the control, you will see the final picture, but when you're moving it, it just goes crazy. The reason is Mathematica has this adaptive sampling mechanism where you are interacting with your graphics. It automatically drops the sample rate so that it will be more interactive, but the quality will drop. In this case, if you want to maintain whole quality throughout the animation, then there's a function called performance score. Let me see, performance score here, the first one, nice. Now, by default, it's called the speed. That's when that adaptive sampling that I just mentioned happens. So you can just use a quality. Then it will try to maintain the quality all the time, regardless of your, So you can see it's much better animation than before. Now, another thing you have to note, to try to figure out, it's actually, in this case, it's okay, but sometimes when your graphic changes, the plot range can wiggle. So, the Mathematica try to zoom into the particular graphics all the time. To prevent that, you want to use a plot range and specific, the explicit range. But in this case, it's okay, so I will skip this. Now, how you're gonna make, for instance, animation file out of it? It's deadly simple. In particular, for the manipulate case, you can just say import, of the file name. In this case, there's a lot of different, the export format we support. And let's see if there's any good animation format here. So we support AVI, and there's the, let me see, SWF, which is flash file. So you can just say import of that image to the image file, the one of the video file, and it just created. And I will use this opportunity to bring more complex ones. So this one is one of the demonstration called the mathematics of tsunami. It's based on to the Indonesian tsunami years ago, and it is actually solving quite complex shallow water equation real time, and you can actually see how it works well. So it's very complex animation. Now, based on this, I create a much more higher quality version of it, and I will try to play the video. I just first skip. It's purely generated by Mathematica. Of course, it's not real time because the quality is quite high, but you can see Mathematica is very capable of creating these high quality images.
This is beautiful.
Right. So I think this answers the question.
No, those are great. Thank you, Sung. All right, let's keep the questions going here. And Vitaly's one for you. The user wants to know how to transform data into a polar plot, like a polar plot of a year's hourly temperatures.
All right, so excellent question. I think what users wants actually is to get somehow, he probably already has temperature data, but I also would like to mention that in Mathematica I don't have them, but in Mathematica we have them built in. And I know, for example, take a look at this line. So weather data will get the data from, for example, for a city's specific geographic location, but I would like to put in a code of a station, of weather station, and obtain a mean temperature, for example, for the whole year, 2007, from January 1st to December 31. And when we execute this line, we get this list of temperatures, where first is the date, and second one is the mean temperature daily. Now, what we have to do is just use the function which is called list polar plot. It will automatically create a polar plot of the list data, but we have to be careful because we don't want to plug in the dates. We just would like to keep, for example, the temperature. So when we execute this thing, we're going to get a scattered list of points. So to make it visually more compelling, we have to add some options here. So let me try this. For example, the options that I will go with will be, first of all, during true that we understand the sequential, the sequence of points, which follows which. We're going to connect them. We're going to put polar axis automatic, and we're going to put polar grid lines and polar ticks. So if we execute this, hold on a second. Again, missing some extra, yes, missing a comma. So if we execute this, we get a very nice circular plot of our data. And basically, this is what the user wants, but I would like to also mention that I just seen a beautiful demonstration, I think, on our site dedicated to the subject. Let me just search the temperature in the demonstration project and see if I can find it. Temperature, not curve, but yeah, here it is. So basically, this is a polar plot of air temperature, and you see this is live in the browser with the help of CDF, and I'm currently changing the daily parameter, and of course the intensity of the temperature changes from night to day, and you can have a beautiful different types of visualization here, and even put different types of degrees of Celsius, etc. I think this answers the user's question. I hope it is.
And if the user wants to find that code, they can go to the
Yes.
demonstrations project, and you just search temperature, and it was up there on the right side, and
Exactly.
they can download the code as a CDF file, and they can run with it, right?
Perfect. Perfect.
Awesome. The Wolfram demonstrations project is something that's very cool, and also a great place to really learn a whole bunch of stuff, right?
Exactly. Exactly.
All right. Well, Brett, another question for you. I'm graphing multiple lines in a graph. It generates lines of different colors. But when I have if command before the function, the lines cannot come with different colors. How do I correct that?
So this is, I think, a very common issue that people run into. The issue is that, say, if I'm plotting a few curves, so sine of x and let's do sine of x plus pi over 2 and sine of x plus pi and sine of x plus 3 pi over 2. And we're going to have this go from 0 to, say, 4 pi, get a couple of periods in there. And all the plots have different colors, and we can trace out a particular curve fairly easily. But if instead of having the list here, I break this out into a variable ahead of time, so my function list is a bunch of sine functions, and then I plot my function list they're all colored. Wonderful. I can't do that. Okay, so we'll clear that, and I need function of list of x there. So here we have that they're all the same colored. And so the solution for this is to wrap evaluate around the list of functions, and then they'll all be colored again. And basically this allows plot to see that my function list is returning a list of things instead of just a single function. And one other note about plot, or not so much about plot, but about the use of evaluate, is that evaluate is necessary because plot is a whole function, so it doesn't evaluate things immediately. Evaluate will need to be the topmost function inside of an argument to plot to have any effect. So if I have, say, tooltip of evaluate of this, I get blue curves and they have the tooltips again. So if I want to keep the separate colors, I need to make sure that, say, that tooltip is inside of the evaluate and that the evaluate is right after the plot. And then we get uniquely colored curves, and each of them has a unique tooltip, and so on.
No,
So
very nice. Quite simple, too. You Sung, ready for another one?
Mm-hmm.
All right. User is using color data within the gradients and color scheme. They said that the palette missed some gradients used in documentation, including topographic. How do I find them?
Right. It's not missing it. It's there. It's kind of hard to find. Well, not exactly, but it's a different category, so we put it in under different categories. So let me show you the first color scheme palette here. So yeah, these are obviously the gradient that you can get from the color. So let me see how you're gonna get all these. Or like you can type the gradients, then it will show the list of gradients, and you can see the image of them by color data, comma image, and mapping that. This it makes it a pure function. Then it maps it through all those names. So you get a nice list of gradient. Now the problem with this one is these are scaled colors, meaning the left end of it start from 0, the right end of it ending at the 1. So that's not the color you want to use for those topographic colors, because it has to be associated with the elevation, right? That's right under this physical. I know it's kind of hidden there, but you can see we have 3 categories of physical color. We have an intention to increase it. Now the problem with these ones are the ranges are all different. So for instance, black body spectrum. The range running from the tooltip shows it from the 1000 to 10,000 K, the Kelvin, the temperature, right? So the left hand starting from 1,000, ending at 10,000. This is the one that the user is wanting, the topographic color. It's named the hypsometric tint, right? It's a hard word, right? It's a map-making color, essentially. What it says is, in fancy way, and it started from -6,000 to 6,000 meters. The order is meter, and it is based on the USGS recommended color spec. Now there's a bezier spectrum. Of course, you can see that it's the wavelengths of nanometers, 380 to 750. So how are you going to use those data? I will grab the one of the elevation data from our database. Doesn't take much time. There's a plot called Lily plot, which can be used to visualize this. So color function goes to, let's say, rainbow. It wouldn't look that beautiful, but let's see it. So it does a rainbow coloring. Now I want to use this hypsometric tint. So first, just typing it correctly is challenging. Let me just insert it, right? Okay. So hypsometric tints. Now there's one care you need to do. By default, Mathematica do something called the color function scaling. What does it mean is that it scales the G values from the bottom to top to the 0 to 1, so that you don't have to worry about your range of the heights and the color functions, because the underlying assumption is you would use gradient color as your color function. Now in this case, it's not true. You really want to use the height values that is originally there. So you say the color function scale goes to false. Then it will actually pick up the original elevation and use the color as a real color. So, you know, it's obviously it's a high elevation, so you can see what it is like this. Now, the reason you want to use, sometimes you want to use color function scaling goes to force is like these cases, you know. So these are two same graphics with the different region. If I put those two back to back, you will see something is a problem. And using that color function scaling essentially true, which is default, I cut the same. The second data set, and let's see how it works. So, oh, kind of small. Let me increase the magnification. So, see, it aligns well, except the color is different, right? Because the second graphics always, the lowest value starts from the red color, which is given in the gradient here, and ending at the high color. So, to avoid that, what you want to use is essentially color function scaling. Goes to force. Then it keeps essentially the you know, color values, the height values of the original plots. So in the end, it will become the same height. So you get the exactly matching, you know, colors. It's very important for elevation data because many times elevation data comes as a patches. It's not single humongous Earth elevation. They have like a small patches of it, and you have to match these colors. So that's when you want to use this color data, you know, the special hypsometric tint colors with the color function scaling goes to false.
Fantastic. No, that's a very cool feature. And if you're tuning in late or you have to leave early, want to pass along that we will have this video available to watch on demand on our website. And we'll also have all the notebooks that these Mathematica experts are using today to show you this. You can find these examples and you can play with them a little bit more yourself. Well, Vitaly, got a question for you here. I would like to plot information from 3 variables on one graph. I'm new to Mathematica and don't know how to start. So help out a new Mathematica user here.
Right, excellent question. So I guess what user actually wants, he would like to put 3 different functions on one graph. And because he only starts, as a great place to start, it's a documentation center. But before that, I will just show the simplest example how plotting several functions on Mathematica graph works. So for example, when you plot single function on a graph, like this sine wave, you just need to put the rest of the function with it into a list. It's a standard Mathematica objects list after the comma. For example, to add more graphs, like these ones, and let's say more frequent, and you get 3 graphs on one plot. But the same logic can be applied not only to plot function, but to tremendous set of all the graphical functions that we have. For example, if you would be just curious and put plot and documentation center, the example, as a second example, will tell him how to actually put 3 different functions on a graph. The same thing can be done, for example, for the surfaces. If you go, for example, to documentation center, the second example there plots 2 surfaces on one graph, and you can add more surfaces. Like for example, you could put 3 of them. Probably he meant 3-dimensional graph here, so I'm just gonna stick sine xy here and get a 3rd surface inside. And of course, the same is valid for the data which is given as a set of points. For example, for the list plot in documentation center, I'm sure here he has an example of a graph that plots simultaneously 3 data sets on the same data plot, list plot, and so on and so forth. Just go to documentation center and you immediately find several examples there at the top, just sitting and showing you how to do that.
Well, this is something that we talked about yesterday. Is, you know, I was watching you guys get ready and, you know, try to brush yourself up on some of this stuff, and you guys use the documentation center a lot, and for a new user, that place can really be helpful, right?
Yeah, I use it all the time myself. I'm not a new user, but it's very, very helpful. We have a very huge documentation center, a lot of information there, so of course it's impossible to keep it all in your head, and you can just always go to options, to settings, and find all that stuff there.
You can find great examples and how to do something,
exactly.
And know a lot of answers to your questions can probably be found there. I know these guys use it all the time too. Well, Brett, I got a question for you. Please comment on the use of legends in graphs produced with Mathematica. Maybe show a few examples there.
Okay, so we have a lot of ways that you can accomplish legends in Mathematica. And so besides so perhaps historically the most significant is the plot legends package, which I'm going to bring up the documentation for it and then completely ignore it. And so we have a package, and it will do some automatic legending for, say, plot, and it knows how to pick out the plot styles that are being used by default, and that sort of thing. It's showing its age a little bit, and so I'm going to, and additionally, it's restricted to working with graphics. And so I'm going to approach legends from a more general approach that will work with plots, 3D, the new graph objects. They'll work. If you have a table of values and you want to create a legend for that, so these will be general approaches that we can use. So I'm going to start with a 3D graphic that I've colored with a color function. And we know in this case that this is going from -1 to 1. And so I'm going to use density plot to create a legend for it. So I'm going to have z go from -1 to 1, and I just have a little placeholder token x to give it some width. We're going to use the same color function. And we're going to adjust the frame ticks so that there are only ticks on the right-hand side. I'm also turning off the padding so that the frame is tight to the color gradient. And I set the image size to make it a little bit smaller than default. So the easiest way, or one of the easier ways to create a legend, is to use labeled. And we can just do labeled with the plot and our legend. And I say I want the legend on the right-hand side, and it looks reasonably nice. With this, I can still rotate the graphic if I need to. I can come in, resize it, and the legend tracks along with it. The other approach that I'm going to look at is the use of overlay, which takes a list of elements and basically draws them all on top of each other. So I'm going to start with my plot, and I'm going to draw the legend on top of that. And by default, this is going to be at the top left corner. In this case, by default, I can't interact with the graphic in the same way. And if I don't want it in the top left corner, there's an alignment option that I can specify. So if I say I want it all the way on the right, and I want it centered, so this is using a -1 to 1 scaled coordinate system. And we can put this over. We'll hook this up to manipulate. At a position. And I want P to go from -1, -1 to 1, 1. Okay, got the manipulate syntax backwards. Okay, how do I get it to the slider? I don't want it in the list. That's right. And I did want -1 to 1. You can tell often I use this particular syntax of manipulate. And so now I can drag this around and say put it down in the bottom right corner where there's not much else going on. So for the alignment option, it's matching up the, so if we look at, so we have this down in the bottom right corner, which means that it's at 1, -1, which means that the bottom right corner of the legend is being aligned with the bottom right corner of the plot. So if I put it into the middle, then it's matching up the middles of each of the elements and so on. So.
Fantastic. No, you're always liking legends. You're a big legends guy. All right, Vitaly, I have another one for you. I want to put two plots in one column so that the y-axis align perfectly. How do I do that?
This.
Oh, sorry, you suck. Did I say Vitaly?
Oh, okay. I didn't expect that. Right. Hey, you mixed the order. Right. Yeah. Yeah. This is a good question. It's, it's very tricky because here's one thing. Mathematica tries to do many things automatically to help you. To help you and to guide you, and you don't have to care about a lot of things. Whereas in this particular scenario, you want to, essentially get your hand dirty and do it manually because that's the one thing you want to do it here. So let me show you the two examples of plots that has a widely different x ranges. So essentially same plot. Now, what the user meant in here is if I increase the range to, let's say, 10,000, then you can see the y-axis are not aligned just because the ticks on the side is not aligned, right? Because it has a much more bigger number. It has 6 digits here, 5 digits here. So now, how are you going to align these two? Let me first try to use I have to match the options exactly the same. So I will introduce a variable called options, and I will include the options that I want to use. But let's say first I want to fix the size of the image. Let's say 400, and then let me think. Instead of using axis, I want to use the frame, which will make it more apparent when you're matching up. And then here's a trick. Mathematica has the function called option called image padding. It adds a padding around your actual image. The problem is it's automatic in a sense that when you have these thing numbers, it adds a padding just enough to include those the thing numbers, right? Now in this case, that's not enough, especially for the first image. You need a more padding to match up with this one. So why don't we fix the padding? And the order is it's a little bit tricky to memorize, but order goes like left and right, bottom and top. So the most concerning part here is the left side. Let's say we give enough pixel. In this case, let's say 60 would be enough, and the rest of them you can just say automatic, so that Mathematica will pick up whatever value it is to pick. Now I'm gonna use all these values as an option to both plots, right? G1 is this, let's say P1. That looks much more nicer. Now, you cannot just put the options because the property of plot is, so if you call function called attribute with a particular function, it says it's a hold all. Means if you put this option as in like option here, what's gonna happen is only thing plot C is just that literally the symbol option, not the inside thing. So you have to evaluate so that it will take a look at inside. So okay, wow, I think I put too much, the padding, but I think it'll work. So same thing. Okay, let's confirm that it really matches up. Column P1, P2. Perfect, right? It's perfectly aligned at the corner. So this is how you do it, So, well, unfortunately, there's no easy way to guess this number. It could be a lot of trial and error, but it's not that hard. Once you get the largest the tick size, then you just probably want to use that value and stick to that number. Another trick here is the column alignment. If both of the function has a different size, well, let me say, plot range image size goes to a little bit smaller. Let's say, right? Still, you want to align these two, right? Now, as you can see, the alignment is perfectly right because the alignment option is left side. But if you see the right, then it will align to the right corner. So that's it.
Fantastic. All right, well, let's keep the questions going. Let's go over to Vitaly, and I actually mean it this time, too. Let's give you one here. A user has a question about they want to create a table from 1 to 250 and having the prime numbers be displayed differently as the rest. And in the show, you'll see some more details here. Vitaly can see that. It'll be a little bit easier to read than me trying to read it.
Okay, so let me try to do that. So basically, first we start from generating a set of numbers, which in Mathematica done with a single command range. And I would like to generate a standard set of numbers from 1 to 250. Now, I would like to pick among these numbers only prime numbers and do something different with them. So I would say that I would like to test whether the number is prime or not. And if the number is prime, I would like to apply, say, some different style to it. So I will start from command if, which will determine whether I would like change the style or not. And I would like to map this command over all the set of numbers. And as a main anchor inside the if, I would like to use prime q, which is going to test my number. And I would like to say this, if number turns out to be, for example, prime q, I'm going to apply style to this number. I would like to make it, for example, orange, bold, and for example, size, let's say 18. Maybe it's too big. Let's make it 15. And also would like to, for example, frame it. Now I will, if the number turns out, the other output of if number is not prime, so I will keep it as it is. So let's see what will happen. Framed. OK, so we got our set of numbers all framed. All the primes I get framed, bold, and increased size. Now I would like to create a table out of this, so I will partition. We have 250 elements, so I will use partition function to wrap it around the code and say I would like to partition it in a row, and every row contains 10 elements. And then after that, I will apply grid to the whole thing to display it nicely. And here I have my table of primes from 1 to 250. And we can obviously see the primes, but you can do something neat. For example, use tooltip to do some other operations on them. Let's say if the number turns out to be prime, you're going to say tooltip, and let's say you're going to yell prime, 3 exclamation points. So let's see how it works. If the number is regular, mouse over gives you nothing. If you roll over the prime, it says that this number is prime. So I think basically it's something like this. This can be a start to do this type of things.
Fantastic. And I know we mentioned it before that we'll be putting these notebooks up to download, and we'll have the video available on our website as well. So you can download that notebook that he just worked on, and you can work on it a little bit and take it to the next level. All right, Brett, I have another question for you here. When I plot a 3D graphics object, is it possible to plot the projection of this object on the 3 or orthogonal coordinate planes? Pardon me. In older versions of Mathematica, such option was available by the function shadow.
Right, so shadow is no more, but there are ways of recreating the effect that it had. So the simplest example is actually I'm going to go to our web page, and I'm going to be looking at the what's new in Mathematica version 8, and there's an example of this in the down here in new statistics visualizations. So here we have a smooth histogram 3D of some statistical data, and we've projected the marginals onto 2 of the faces. And if we look at the input, it's a little bit involved, but we can, actually, let's start up at the top. I'm going to be copying stuff into Mathematica for just a moment. So we're going to get our data. We're going to get the projection for the back face. We're going to get the projection for the left face. And then we're going to get everything else. So let's go ahead and evaluate these just to, let me increase my magnification a bit. So we're going to be looking at the old faithful data, and that loaded nice and quickly. And we're going to go ahead and see what these look like. So for some optimization purposes, we are looking at, ignore the black, I think. We're rasterizing the graphic, and we're going to get the values out of that image, and we're going to create a texture for the 3D object from that. And now we'll do the left side, and we don't need to look at the result there. And so now we have a smooth histogram 3D with a color function and some plot ranges set, and we're setting the lighting to neutral to have, so that the, that should work automatically, but anyway. So that the colored lights don't interact with the colors from the color function. And then we're setting some font sizes and image size and that sort of thing. And if we just take a look at this graphic real quick. We'll make my window a bit larger. We see the main plot that we're going to be working with. Onto this, we're going to add 2 polygons. One is going to have the texture for the back surface, which is going to show up here behind my plot on the right and at the back. And we're using the back picture that we generated as a texture, and I'm going to create a polygon in scaled coordinates in the 3D graphics scene. So this is going to go from 0, 1, 0, so 0, 1, 0 down here, to 1, 1, 0, to 1, 1, 1, to 0, 1, 1. And then we're going to do the same thing for the left face with a different texture and a different polygon in scaled coordinate systems. And the polygons have vertex texture coordinates set to say how to map the image that we're creating for the texture onto that polygon. So we're going to put the bottom left corner of the picture at 0, 1, 1, the right bottom corner of the picture at 1, 1, 0, and so on. And so now if we put this all together, then we get our 3D smooth histogram with the marginals plotted onto the left and back faces. And this generalizes to the top face, front faces, wherever you want it. If you are using other coordinates, you could have whole slices of projections going through your plot, whatever. So there you go.
Fantastic. Well, stick around. We're about to wrap things up here in a few minutes. We will have a short open chat for you to provide some feedback. There'll be a quick survey. We would love to hear what you thought of the last hour. So let's get to one final question here before we kind of wrap things up. And I guess Yusung or Vitaly, or both, you can handle this one. How can I visualize a surface as a wireframe?
Vitaly can handle that.
Yeah,
Vitaly, go
yeah, sure. So in Mathematica, there are quite a few options to solve, I think, many problems, and this is just another example of that. We will start with a little bit more cumbersome way. So for example, because you need to put several curves in 3-dimensional space parallel to each other, you can think about immediately contour plot 3D. So let me try to find that function, contour plot 3D. I use Ctrl-K as a hint for myself because I use it often. Now let's see. We'll probably, actually I'm looking for parametric plot 3D. Not contour plot 3D, parametric plot 3D. So let's see what examples we have here. So for example, this wire, okay? Let's take this example with a wire. And I would like to make this function to be constant, for example, 1. And I get a sine wave in 3-dimensional space. So for example, the simplest, one of the simplest way to put a few wires close together to take range, for example, up to 10. And I'm going to replace this thing with a cache tag which represents a variable and map this over a list. And I will get immediately a set of wires placed parallelly in a space. But probably the easiest way to do it, it's a little bit different way, Imagine that you have a surface, already given surface, right? So it could be, for example, plot sine of xy with range x goes, say, -3 to 3, y -3 to 3. So you have your surface. So you see already mesh is on a surface. So you can use that mesh to create your wires. To do that, first of all, you have to remove the surface itself. So plot style goes to, I think, none, right? And now you have to remove, for example, one of the orthogonal meshes, x mesh or y mesh. And to do that, you have to use something which is called mesh functions. And let's take a look at it in the documentation. I remember, yeah, first example. Here you see that on this nice plot, three-dimensional plot, the mesh function will take only third argument, and it creates meshes which go like slices orthogonal to y coordinate. We can do the same with any coordinate. And say we would like to have coordinate number 2. We immediately got a parallel set of parallel lines, and I would like to increase the number of these meshes. And here you go, with the parallel wireframes displaying the surface.
Fantastic. Well, that will do it for the live questions today. Stick around again. We have a quick survey for you. We'd love to hear some feedback. There'll be a brief open chat too. So stick around for that in a few moments. So before we wrap things up, any final comments, guys, on the topic of visualization?
Yeah, I have one. So I got a lot of question about, how 3D graphics works, especially about lightings and viewpoint, right? How you set up the camera and how, what's the best way to look into it, and it's not really that complex topic, but our documentation is nice, so I will show you a good way to start it. Let me see. In the documentation, right? If you go to the lighting section, it has a really, really long description about how lighting works and everything. So you should take a look at it. And another good source for this is our training course. I'll just quickly go there. There's a graphic training course provided for the, the general Mathematica section. Just try this out. It has a lot of good information in there. So, especially regarding, you will see this nice picture. There is a bunch of a nice way, interactive way to play with it. So I would highly recommend this course for anybody who's interested in 3D graphics.
Fantastic. Well, I want to thank a few people, everyone working behind the scenes here, making this look as great as it is and making it sound nice, and all the questions getting fed to us. Thank you to all of you. You guys know who you are. I want to thank my colleagues, Yusung Cheng, Vitaly Korov, and Brett Champion, but most importantly, want to thank you, the Mathematica user, for spending an hour with us here this morning. Hopefully you learned something. I know I did. So for Yusung, Vitaly, Brett, and myself, Zach Parcell, thanks for tuning in to Mathematica Experts Live. Have a great day.